Hey class, I wanted to make a video for this problem on the workshop. So what we have here, again, is a little bit tricky. Let's think of it this way. Imagine you're standing down here on the ground, here's you, and you're holding this frisbee preparing to throw it. So you initially start in a circumstance where the frisbee is at rest with no rotation, no translation. You're then going to swing it, and over the course of half of a second, you're going to get it accelerated so that it's now rotating but also translating, and you release it, and then it's going to fly up to some maximum height up here. So let's call this point 0 when it starts, point 1 here when you release it, point 2 up here when it's at its max height. Now, if you've thrown a frisbee much, what you'll realize is when it reaches its max height, it's going to be continually rotating. If we ignore air resistance, there's nothing to slow its rotational motion, but its translational motion will have gone to whatever its velocity is down here at point 1 to a velocity at point 2 of 0 because it's not not translating any longer. And then at point 0, your velocity would also be 0. Now at your omega, your angular velocity at point 0 would be 0 because you haven't thrown it yet. Your omega at point 1 is some value that you don't know, and then your omega up here at point 2 is going to be the same as point 1, but you still wouldn't know what it is. So that's kind of the big picture of what's going on. Now, to think about part A, it's a little bit weird, right? We're asked to find that omega value, the angular velocity, omega 1 or omega 2, since they're the same, right? It's asking what is that angular velocity, and all we're told is that it's given the act of throwing it, so from 0 to 1, your act of throwing it is giving it 75 joules of energy. We're given the dimensions and size of the frisbee, and then we're told that it achieves a height of 25 meters. So again, if we call h2 the height up here, this is 25 meters above the ground, so that assumes that h0 and h1 we can call 0 meters. All right, so this immediately should make you think of conservation of energy. Energy at point 1 plus any work non-conservative equals the energy at point 2. At point 1, your energy is 75 joules. Again, a combination of kinetic rotational and kinetic translational, but we're given the total value. If we're ignoring air resistance, there's no work non-conservative, and then at point 2, it's going to have a combination of gravitational potential energy and the rotational kinetic energy from its rotational speed, 1/2 I omega squared. So this omega value is what you want. You're given the height, you know the mass of the frisbee. So as long as you can figure out I, then you can get the overall total omega that you're looking for. Now your I value is the I for the total I of the frisbee, so it's going to be a combination of I for the ring portion plus the I value for the disc portion. So you just need to make sure to find I for the ring, I for the disc, add them together, and then you should be able to find omega. So I'll leave that to you all to figure out. Then for part B now, when you're asked to figure out what its angular acceleration is while being thrown, now you're analyzing from point 0 to point 1 in time, no longer looking from 1 to 2 as we did in part A. So if we're looking from 0 to 1 here, what you're going to be doing then is thinking about kinematics. See, we know omega initial is 0. We know omega at point 1 is the answer that you got in part A, and we're given the time of 0.5 seconds, so you should be able to find alpha simply using kinematics. Omega final equals omega initial plus alpha times time. And then for part C, you're also being asked to look at from 0 to 1 because you're asking the torque that your wrist is applying to the frisbee about its center of mass while you're in the act of throwing it. And so for that, you can look at some of the torque equals I alpha, knowing that the torque can be thought of as a force multiplied by lever arm distance when you're asked to find the force. So I'm going to go ahead and stop there. I hope that's helpful, and I hope you all have a great day.